Hey guys, sorry I couldn't be in class today, but I wanted to make sure you got your lecture in. So this is your lecture on conservation of energy. Get as much as you can from this, and we will make sure we go over whatever questions you have when I'm back on Monday. So conservation of energy. First, we need to define a few vocabulary terms. First, energy is the ability to do work. So we've already talked a lot about work, and really work and energy are kind of interchangeable. Both are measured in joules. When you do work on an object, then that object can have some energy. So the types of energy that an object can have are either kinetic or potential. Kinetic energy, which we'll represent with a capital letter K, is the energy that an object has because it is in motion. We talked about this one already. It's equal to 1/2 mv squared. The second type of energy that an object can have is potential energy, which we will represent with a capital letter U. And this is the energy of configuration. We're going to talk about two different types of potential energy: gravitational potential energy and spring potential energy. In either case, potential energy has the potential to change back into kinetic energy, or the kinetic energy of motion. If we're talking about gravitational potential energy, then this is the energy that an object has because it is off the ground. If I lift a pen up above the ground and I hold it there, then I have done some work to lift this object up, and that work is now stored as potential energy in that pen. If I let the pen go, it's going to fall back towards the ground. And this potential energy is going to convert into kinetic energy as this falls. Right as it hits the ground, all of that energy is then kinetic energy. Conservative forces are ones whose work can be stored as potential energy. And the potential energy can then be converted back into kinetic energy. So as we just described, a conservative force, an example of conservative force, would be the gravitational force. I do work to lift my pen up off the ground, and that energy is then stored as gravitational potential energy. When I let that pen go, that potential energy is going to convert back into kinetic. So the gravitational force is an example of a conservative force. Spring force is also a conservative force. I do some work in stretching a spring, just like your maths did in the Hooke's Law lab. I do some work in stretching a spring, and then there is potential energy stored in that spring. When I let the spring go, it's going to start moving, and that stored spring potential energy will convert into kinetic energy. Non-conservative forces are, of course, the opposite of conservative forces. Non-conservative forces are those whose work is not stored as potential energy. For us, this will be friction. Okay, friction is an example of a non-conservative force. When friction does work, energy, we say, is lost to our system. It's not really lost. Most of the time, it's converted to heat. But that's a non-conservative force. Potential energy is only associated with conservative forces. So we're going to talk about gravitational potential energy and spring potential energy. These are the formulas that we're going to be using to calculate gravitational potential energy and spring potential energy. Our formula for gravitational potential energy, U sub g, is mgh, where m is the mass of our object, g is the acceleration due to gravity, 9.8 or 10 meters per second squared, and h, capital H, is the height above the ground. Most of the time, this will be the height above the ground. You're going to set ground level as 0, but really it's the height above whatever you set as your 0 location in your problem. Right below, I'm just showing you the units here. So mass is in kilograms, g is in meters per second squared, height is in meters. This gets us Newton meters or joules. Potential energy, just like kinetic energy and work, is measured in joules. Gravitational potential energy can technically be positive or negative, depending on if our object is at a positive or negative elevation, so above or below the ground, or really above or below what we've set as our h equals 0. The second type of potential energy is spring potential energy. This formula should look familiar because we derived this formula for spring potential energy in our Hooke's Law lab when you took the integral of kx, or the integral of the force, to get work. So this formula is the work done in stretching a spring a certain distance x, which is now the same as the energy that is stored in it. So again, I do some work to stretch a spring a certain distance, x, from its unstretched length. The work that it takes to stretch that spring is 1/2 kx squared, and I now have 1/2 kx squared, that energy stored as spring potential energy. K is our spring constant in newtons per meter, and here again we have K in newtons per meter. X is x squared, so that's in meters squared. That gets us Newton meters or joules. So spring potential energy also measured in joules. And remember that friction has no potential energy function associated with it. Our formula for conservation of energy is a general formula that we're going to be applying to our specific situation. So when there are no non-conservative forces acting, really practically for us, this means in the absence of friction, the total amount of mechanical energy in a system is conserved. Mechanical energy refers to kinetic energy and potential energy. Again, mechanical energy is just kinetic and potential energy. So mechanical energy in a system is conserved when there are no non-conservative forces acting. Energy isn't created or destroyed. It's just transferred between different types. So we'll start with either potential energy or kinetic energy or both. And then afterwards, our system will end with the same amount of total energy, potential and kinetic. So again, the initial potential energy of our system plus the initial kinetic energy of our system is going to be equal to the final potential energy plus the final kinetic energy. For potential energy, we have two options. We can have gravitational potential energy, spring potential energy, or both. And then we can have kinetic energy, 1/2 mv squared. Energy is really just another way to look at the problems that we've already solved with Newton's laws and forces. We're going to see this in our first example. We have a ball tossed straight up at 10 meters per second, and I want to know how high above the release point it goes, and then how fast it's going at a height of 3 meters. If I asked you this problem 2 months ago, you would have told me how to solve this using kinematics equations. But we're going to use energy instead. So our conservation of energy formula says that our total initial energy is equal to our total final energy. If I'm tossing a ball straight up at 10 meters per second, initially this ball only has kinetic energy. So I'm going to adapt my general formula here to the specific situation that I'm dealing with. I don't have any initial potential energy because this object starts on the ground. I just have initial kinetic energy. So that's my total initial energy. This is going to equal the total energy after. And afterwards, we're looking at how high above the release point does it go. So this means at the highest point. I know at the highest point, when an object is in free fall, it has a velocity of 0. So at the highest point, we're dealing with only potential energy. So in this particular problem, my initial kinetic energy is going to equal my final potential. Using my formulas, I have 1/2. Sorry, my stylus is not working very well. We have 1/2 mv initial squared is going to equal my final potential energy of mgh. Notice that the masses cancel out. So I've got 1/2 of my initial velocity, which is 10 squared, equals, it's a squared, good enough, equals gh. What does that get me? 10 squared is 100, and half is 50 divided by 10. This object goes up to a height of 5 meters. So you can see how this is even a little bit easier than using your kinematics formulas. We just have to set our initial energy equal to our final energy. So for the second part of the problem, which I'm going to do up in the right-hand corner of the screen, we have how fast is it going at a height of 3 meters. Again, I'm going to use energy, and I still have initial energy is all kinetic. I'm still saying that my initial position is right when we toss this ball straight up at 10 meters per second. So we're on the ground. We have only initial kinetic energy. At a height of 3 meters, that's somewhere between the lowest point and the highest point. So we're going to have both potential energy and kinetic energy. So I can plug in my formulas. 1/2 mv initial squared is equal to mgh plus 1/2 mv squared. Again, all my masses cancel out. I've got 1/2 times v initial, which is 10, squared, is equal to g. I know that I am at a height of 3 meters. That is now my final location. That's a parenthesis. Plus 1/2 v squared. And you can use this formula now to solve for this velocity. Again, the total energy is always the same. So my initial energy is going to equal my final energy at any location. We're going to go through these slides when I come back. They're supposed to have little graphics, and they show you how kinetic energy becomes potential energy or how potential energy becomes kinetic, but we'll look at them later. This is the same idea with the swinging pendulum. Here's our second example. We have a mass that's released from rest and slides down a frictionless plane inclined at 70 degrees to the horizontal. I want to know what the speed of the mass is after sliding along the incline a distance of 3.5 meters. Again, this is a problem we know how to solve. If I'd asked you this a couple weeks ago, you would draw your free body diagram, you'd write your Newton's equation, you would find the acceleration with Newton's second law, then you would use a kinematics equation to figure out the speed at the bottom. Totally doable, but it is a lot easier when you look at it from the lens of energy instead. So we're still going to draw a little picture here. I have my mass at the top of this incline, and it's going to slide down a distance of 3.5 meters. It's released from rest, and this angle here is 70 degrees, and I want to know how fast it's going at the bottom. Again, thinking about this in terms of energy, the total energy of my system initially is equal to the total final energy. So I'm going to look at this and say, what type of energy does this thing have when it starts? Well, at the top here, it is at some height, so it's above the ground, so I definitely have initial gravitational potential energy. And it's released from rest, so it's not moving, so I do not have any initial kinetic. So my total initial energy is all gravitational potential. Afterwards, we want to know the speed of this mass when it gets to the bottom. So since I'm on the ground, I have no gravitational potential energy. All of that energy becomes kinetic. Plugging in here, I've got mgh initial equals 1/2 mv final squared. Again, those masses cancel. G is 10. Now be careful with that initial height. The distance down the incline is 3.5. But that is h initial, the actual vertical height. That's what I care about. So using my triangle, that would be 3.5 sine of 70 equals 1/2 v squared. Again, you would just plug this into your calculator and figure out this final velocity. Way easier than doing all of those steps with Newton's laws and kinematics. So a little reminder with what we did a couple days ago with our Hooke's Law lab. We derived this equation here for the spring force, which said the spring force you had was equal to kx. That negative sign just means that this force is a restoring force. You won't usually have to use the negative sign when you're actually solving this equation, but as a restoring force, what that means is that the spring force is always trying to push or pull your mass back to its equilibrium position. So if our spring is compressed, as it is in the first diagram here, the spring force is trying to push it to the right. If our mass is at equilibrium here, the spring is not trying to do anything. In the third diagram, if our spring is stretched, the spring force is trying to pull it to the left or back towards equilibrium. So F sub S is our spring force in newtons. X is where we are located, or our displacement from equilibrium. And then K is our spring constant. Thinking about springs from the lens of energy, spring potential energy will always be positive since it's equal to 1/2 kx squared, and that x is squared. So stretching something a certain distance and compressing that same spring that same distance will give you the same potential energy. When we are thinking about springs and energy, there's a couple of intuitions or things that you should recognize. At equilibrium, right here, when I'm calling 0, 0 on my number line, that's where our spring is moving the fastest. So it's actually easier to think about it as we are first stretching our spring out to some amplitude A. That's just a location. We're stretching it and we're holding it there. At this location, our object is not moving, so the kinetic energy is 0. And the potential energy equals 1/2 kx squared, or in this case, since we're stretched to distance A, it's equal to 1/2 ka squared. You let this spring go. As you let it go, that potential energy starts to turn into kinetic energy until right at your equilibrium position, you have the most kinetic energy equal to 1/2 mv squared and no potential energy because that spring is not stretched or compressed at all. Then the opposite happens on the other side. As it passes equilibrium, we lose kinetic energy and start to gain potential energy as this spring compresses until we end up on the other side of our number line at negative A0 and have that same potential energy of 1/2 ka squared. Again, our spring stops moving at this endpoint, and then it's going to keep doing that back and forth, or oscillating back and forth. So let's use this to solve our last example. My wonderful pictures here. This is a mass attached to a spring of spring constant K, and that spring is compressed a distance x from its equilibrium position, or really from its unstretched length. So we've compressed that mass, and then we're going to let it go, and it's going to travel first along this horizontal and then start to go up the hill. And I want to know what the maximum speed of the block is. I'm going to think about this in terms of energy. Total energy of our system is conserved. So our total initial energy is going to equal our total final energy. Initially, this mass is compressed and not moving and on the ground. So we are starting only with gravitational potential energy. I'm going to put the little subscript of G. As we let this thing go, at its maximum speed is going to happen right here at this equilibrium position. With maximum speed, we're going to have all kinetic energy. So that's what our conservation of energy equation looks like. I can plug in. I've got, I messed up here, guys. Sorry. That is clearly not gravitational potential energy. That is spring potential energy. It is on the ground, and it is compressed. The spring is compressed. Almost got through the whole lecture with no mistake. That is spring potential energy, sorry. And that's going to turn into kinetic energy. Spring potential energy is equal to 1/2 kx squared. X being the distance our spring is compressed right here. And that's going to turn into kinetic energy, 1/2 mv squared. I'm trying to find this maximum speed v. the 1/2 cancel out. So v squared is going to equal kx squared over m, or v equals the square root of kx squared over m. That will be our maximum speed. In the second part, what maximum height does it reach? Again, we are using conservation of energy. And you can say that your beginning location is either when this mass is compressed by the spring here, or the spring is compressed by the mass, rather. Or you can say that your initial position is right here, what we just found, that 1/2 mv squared. Either way, it doesn't matter, because the 1/2 kx squared at the very beginning is equal to the 1/2 mv squared right when it's going the fastest, which is then going to be equal to the energy at this max height. So either way, I'm just going to say that what I want to say is my beginning location, or my initial energy, is when the mass is compressing this spring. So again, we start with spring potential energy. But this time, as this object goes up this hill, some point up here it's going to run at a speed at its max height, h. And at that point, it's going to have all gravitational potential energy. So that is my conservation of energy equation for this problem. Spring potential energy, 1/2 kx squared, this time equal to mgh. So looking for that max height, the height is going to be equal to 1/2 kx squared over mg. If you had numbers, you could plug in, but we don't, so we're just leaving it in variables. The last part of the problem said, what is v when h equals blank? It's really asking for you to come up with a generic formula to be able to solve for the velocity when we are at any height up here, because at any point up on this incline, it's going to be moving and it's going to be off the ground. So again, we'd set up our conservation of energy equation. Still at the beginning, we have all spring potential energy. That is always our total energy, 1/2 kx squared. And we're going to be at some height h, so we're going to have gravitational potential energy, and we're going to have kinetic energy. So you would be given that velocity, and you could use this to figure out what height you are at. That concludes our lesson on conservation of energy for now. You have the conservation of energy problems, which are on the back of PS3 to work on. You also should be getting a handout of PS4. Do as much of these as you can, and we will talk about them next week.